we toss this coin until the first head appears. X is our random variable, which is the number of tossings. Including the one with head. X can take any positive integer value. Let us find the distribution of X. Probability that X takes value k equals to the following. It is the probability of sequence like tail, 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 and so on, tail, head. And here we have k minus 1 tails, and the last one, k's position, is head. The probability of outcome of this kind can be calculated by a product of the corresponding outcomes that we have tail at some particular position or head at some particular position. So, if we assume that probability of head equals to p, then this probability equals to 1 minus p to the power k minus 1 times p. This part corresponds to this part, and this p corresponds to this part. Here, k can be any positive integer number. Another distribution with infinite number of values is a very well-known Poisson distribution. Poisson distribution is a distribution of random variable that can take any non-negative integer value from 0 to infinity. It can be used to model a value that is equal to number of, for example, visitors of your shop during some period of time, for example, during the day. It is possible that during some period of time you have 0 visitors, if you're unlucky and it is a bad day for you, or it is possible that you have 1 visitor, or 10 visitors, or 100 visitors. You don't have a priori any upper bound for the number of visitors, so theoretically it can be any positive number. Another example, assume that you're a call center and you want to know what is the number of calls that you have to get during some period of time. Again, you don't know in advance how many people will call you during some period of time. So you can use Poisson random variable to model this number. To specify Poisson distribution, we have to pick some real number lambda, which is just arbitrary positive real number. And then we get the probability that our random variable takes value k, and this probability equals to the following thing. This is lambda to the power k over k factorial times exponent of negative lambda. This formula looks a little bit cryptic. I will not discuss in details how to get this formula as a limit of binomial distribution under some conditions. I will leave it as an exercise if you are really interested in. But what I want to say is that this Poisson distribution is really useful in practice, and several methods of probability modeling use this Poisson distribution. For example, there exists so-called Poisson regression. Let us discuss how can we sample random variables using Python. First of all, we will sample from discrete random variables that are explicitly defined by the corresponding values and their probabilities. To generate a random variable that is given by values and probabilities, we can use function choice from NumPy random model. So first we have to import it. Note that this function choice is imported from this model and not from model random, because it is a different function. So let us discuss how this function works. Let us assume that I want a random variable that takes values 1, 2, and 4 with probabilities, for example, 0.2, 0.5, and 0.3. Then I can write this command, and every time I invoke this command, this function, I get a new generated number that follows these probabilities. And if I do it several times, I will get about 1/2 of times number 2, because the corresponding probability is 1/2, and about 3/10 of times I will get 4, and so on. Let us check that it is indeed true. To do it, we have to write a function that will count frequencies of values in some array or in some list, and we can use dictionaries to do it efficiently. So let me introduce function count frequencies. We get some data, which is something like list or NumPy array, and we will get option relative, which is by default false. This option will guide us which kind of frequencies we want to calculate. By default, frequencies are just number of times that we have some value in this list, but if we get relative true, then it is number of times we get this value divided by number of all values. So we need some dictionary, and we have to iterate over all elements in our data, and for each element it can be either already counted at least once, then it will be in this counter, or if we meet with this particular element for first time, we will not have this element in this counter. So we have to check this condition. If element not in counter, it means that we get this element for the first time. Then we have to put counter of element to be 1, and otherwise we have to increase number that we have in counter at the position with key element. Actually, this line can be rewritten shortly in this way. Now, if relative is false, then we can just return this counter. But if relative is true, then we have to do some post-processing. So we have to do the following thing. If relative, then we have to iterate over all elements in this counter and divide the corresponding value by the len of our data. So we have this thing. Actually, this can be written shortly in this way. Now we have to return the counter. Let us check that our function works. We see that this function gives us 3 items which are equal to 1 and 1 item which is equal to 2, which is correct. And we can also get relative, and we see relative frequencies. Now we will use this function count frequencies to analyze the behavior of this function. I will just copy paste it here, and I want to invoke it several times and record the results into some list. This can be done easily with list comprehension. I just invoke the same function and I do it several times. For example, 1000 times. Now I have a sample which is a list of 1000 elements, and each element is the result of this function. Now let us find frequencies of values in this sample. This gives us absolute frequencies, and we can add parameter relative true to get relative frequencies. And here you see that relative frequencies in our sample is very close to these probabilities. That is expected if our random number generator works. So we see that we have ones which are about 0.2 of all number of elements in our sample. And the same holds for twos and fourth. For fourth it is a little bit different, but that's fine with this number of elements in the sample. We can increase this number and then we can recalculate the corresponding frequencies, and you see that the larger sample we have, the better corresponding relative frequencies are closer to these probabilities. So it works. Moreover, in fact, instead of using this list comprehension, we can just ask this choice function to give us a sample. We can just add parameter size, which is sample size, and in this case, output of this choice is NumPy array, which is just like this list. Now let us add some visualization. To do it, let us import matplotlib pyplot, and let us draw the bar plot that corresponds to the frequencies that we get. To get matplotlib images, I have to invoke magic command matplotlib online, and then I can use matplotlib bar to draw the corresponding values. Frax keys for x values. I have to put two lists here. In first list, I enumerate all values that I found in my sample, that is Frax keys. And in this list, I put the actual values of frequencies. So we can draw the corresponding figure, and it looks like this one. And you see that we have number 1. Here, the height of this bar corresponds to the frequency we get, and the same with number 2 and number 4. We will use this kind of visualization to study random variables that are generated using the function count frequencies later for different examples of random variables. Previously, we sampled values of random variable that is explicitly defined by providing its values and corresponding probabilities. But for well-known distributions like binomial or Poisson, we don't have to calculate these probabilities by ourselves, because it is already done by developers of libraries that we can use from Python. Let us discuss how can we sample from such random variables as binomial. It can be done in different ways, and the simplest way is to use NumPy random model, and let me show how to do it. From NumPy random import binomial. This function generates a random variable from binomial distribution, and to make this generation we have to specify n, which is the number of trials or number of coin tossings, and p, which is the probability of success, or probability of getting head, if our random variable is number of heads. For example, we can say that we toss coin 10 times and probability of success is order 3. Then every time we invoke this function, we will get the corresponding binomial number. You see, for example, that we have some small numbers in general, because the probability of success is smaller than 1/2. Let us use our function that we wrote previously to analyze the distribution of the samples that are given by this function. Again, as previously, we can add parameter size and get not a single number, but an sample from this distribution. And we can use the function that we defined previously. Let me recreate this function once again. And now we can save the result of this binomial to some variable, like sample. And we can count frequencies of this sample. For example, relative. To test how good is our generator, this binomial function, we have to find the actual probabilities of all the values that we have in binomial distribution. This can be done by some explicit calculation using formulas that we discussed in the lecture. But it is also possible to use a function that will calculate these probabilities for us. This function can be found in SciPy stats model, and this is done in the following way. from scipy stats import binom. In fact, this function defines the corresponding distribution. So let me create this distribution by invoking this function and providing number of trials, number of coin tossings, and probability of success, probability of head, just like here. And now I can use this object to get some properties of this kind of random variable. For example, I can get values of probability mass function of this random variable at different points. For example, probability mass function at point 1 is this one. And you see that it is quite close to our frequencies that were calculated for our sample. To make this more exact, we can increase sample size, and then the corresponding frequencies will be closer to the expected frequency, which is given by the corresponding probability. For example, this value of probability mass function at 1 gives us this number, and the obtained frequency is this number. Now let us visualize the frequencies that we get here and corresponding probabilities. To do so, I have to invoke matplotlib again. And to draw a graph of this probability mass function, I have to introduce a value x that will define the range in which I will draw this graph. To make this range, I need a function from NumPy, and let me add one more import NumPy as np, and then I will use arange from 0 to 10 with step O.1. Then x is just an array of evenly located numbers on segment from 0 to 10 with this step. So we see the result of this operation. And now we can use it to plot the corresponding graph. PLT plot. I have to put values of x here, and as the second argument I have to put the corresponding values of a function, which is pmef, and I can put here not only one number but an array of numbers, and this function will be calculated element-wise. So for each element here I calculate the corresponding PMF. Let us look at the result. Okay, you see these spikes. This is because here the value of the function is 0, because our random variable x capital cannot take these non-integer values. And we have these spikes at integer numbers. So it is probably better to use a different visualization here. Now every point on this graph just corresponds to a pair of x and y here. So we can draw two graphs. First graph, which is given by this probability mass function, and another graph which is given by our sample, the bar plot like we plotted previously. To do so, we have to make a PLT bar, and let me save these count frequencies somewhere. And now I can just plot freq keys for x values, I have to convert both of them to lists. Otherwise, PLT bar will not work. And let me use different color, for example, here. Here you see that the probabilities that we have from theory are a very good approximation to the relative frequencies that we obtained by our generation. Also, we can investigate how changing of the values of n and pi will affect this graph. Let me copy these two lines, and let me copy some other lines. So again, we need this random variable, and we need this sample. To avoid changing one value in different places, let me introduce variables n small, which is number of trials, and p, which is probability of success, and put it here. And here. So now the result is the same, but we can change, for example, probability of success and get different pictures. You see, for example, that when you increase probability of success, you will get much more cases when the corresponding value is closer to 10. We can also change this n, number of trials. For example, we can put 5 here, and you see that it affects the graph. The maximum possible value of our random variable is 5. And we can also change this sample size. For example, if we decrease it to 10, then you see that the obtained frequencies can be different from the probabilities. But as we increase the sample size, the correspondence between frequencies and probabilities becomes stronger. And if the sample size is 10,000, we almost have no difference between these red points and the top level of these rectangles. And if we increase the sample size further, we have even better correspondence. So, in this way, we can analyze any random variable that is generated by NumPy. Actually, there are a lot of predefined random variables. For us, it can be interesting to study Poisson or geometric distributions. During this week, we discussed the notion of random variable. Random variable denotes a value that depends on the result of some random experiment. Natural examples of random variable is payout in some lottery or some other gambling. There are two main classes of random variables that we will consider. These are discrete and continuous random variables. Discrete random variables can take only discrete values. I mean that we have finite or countable number of values that our random variable can take. But continuous random variable can take any value in some segment of real line, for example, from 0 to 1, or all possible real numbers as their value. During this week, we discussed only discrete random variables, but we will discuss continuous random variables later. Discrete random variables can be described by their distribution. It means that we say which values can this variable take and with which probabilities. For example, we consider it binomial random variable, which is the number of heads obtained in a series of coin tossing with not necessarily fair coin. So the probability of head can be not 1/2 but some other value. This is an important example of a random variable that will be used later. We also discussed the notion of expected value of a random variable, which is in a sense average value that random variable takes, and during the calculation of this average we take into account probabilities with which different values are taken. We also discussed variance, which is the deviation of our random variable from its expected value. Actually, it is an expected value of square of deviation of random variable from its expected value. On the next week, we will continue discussing of random variables. But now we will discuss several random variables. We have to do it because we model our data with random variables, and we assume that there is some relation between different variables in our data. For example, between age of a person and their income, or something more obscure. And our methods of data science and machine learning can uncover these hidden relations between variables and use them to make useful predictions. To model such relations, we have to consider systems of random variables that can interact with each other in some sense. So this will be the main topic of the next week. Previously, we discussed random variables. Now, we will consider systems of random variables. It means that for a particular random experiment, we will consider several random variables that are associated with this experiment. And we will study the relations between these random variables. To begin with, let us consider an example. Let us return to an example with casino. As before, Alice bets $100 on red, and at the same time another player, Bob, bets $100 on black. Now we have Alice's payout and Bob's payout, and these are two different random variables which values are defined by the result of the same random experiment, spinning of the wheel of this roulette. We also see that these random variables are related to each other. For example, if we know that Alice won $100, then it means that the outcome of our experiment gives us a red number, and it means that Bob cannot win and he loses $100, and so his payout is -100. So we see that there is a relation between these two random variables. Now consider the third player, Claudia. Claudia bets $100 on the number 32. So she wins only if the result of our experiment is exactly number 32. We have new random variable that is related to, for example, Alice's payout. If Alice wins, then it means that the outcome that we have is red, and it increases chances of Claudia to win because 32 is red. Now we see that there is some kind of relationship between this random variable, but this relationship is not deterministic. We cannot answer exactly what will be Claudia's payout, even if we know Alice's payout. Finally, let us consider Dan. He bets $100 on red, but on different roulette, because two roulettes are independent to each other. We cannot use any information about Alice's payout to say something new about Dan's payout. So these two random variables are independent of each other. Now let us look how a similar reasoning about random variables can be applied to problem of machine learning. In machine learning, we have data that looks like this table. And every column of this data have some value. But we can assume that these columns are random variables because, for example, if we look at the first row of this table, we think about some particular person that gave these answers to some questions in questionnaire. And we understand that this particular person was chosen randomly from some population. And the same thing holds for every row of this table. So we can think about every row of this table as a realization of some system of random variables. And we can try to find some relations between these random variables. For example, if we see a person with large age, we probably expect that their income will be also large compared to some person with low age, just because very young persons usually do not have large incomes. In any case, we will think about these variables as a kind of random variables. For example, because we don't know exactly what is the income of a particular person of age 21. Now, let us discuss our plans for today. First of all, we will discuss what kind of relations between random variables exist. And we'll create new random variables from the existing ones with different transformations. Then we will discuss how to describe system of random variables. This can be done with so-called giant distribution. Then we will discuss what independence mean in context of random variables and why it is sometimes very useful to have independent random variables. Finally, we will discuss notion of covariance and correlation, which are important for practical applications. Today we will study systems of random variables. What do we mean under system of random variable? Let us consider some random experiment. We know that to define random experiment, we have to specify probability space that is associated with it. It means that we have to define omega, which is a set of elementary outcomes, and we have to define probability of every outcome. Now let us consider two random variables associated with this random experiment. Mathematically speaking, it means that we have to define two functions from omega to space of all real numbers. Now we can say that x and y are our system of random variables. What does it mean that it is a system? These two variables can interact with each other. It means, for example, that if we know something about x, we can say something about y, and vice versa. So today we will study these interactions between such variables. Let us discuss how can we create new random variable from existing random variable. So we have x, and we want to define y using this variable x. This can be done in different ways, and let us discuss first some important examples. Let x be some random variable, and let c be some constant. So c is just a number like 2. Now we can consider new random variable y, which is equal to x plus c. Let us consider example. Let me assume that I have the following probabilities: O.2, O.5, O.3. And let me assume that x takes value -1 with probability O.2, 3 with probability O.5, and 4 with probability O.3. Then we can consider variable y, which is equal to x plus 2, and it means that with probability O.2 it takes value 1, with probability O.5 it takes value 5, and with probability O.3 it takes value 6. So we have new random variable that is connected with the initial variable x. It may be useful to think about probability mass functions that are associated with this transformation. Indeed, let us consider probability mass function for variable x. Let us draw the graph of this probability mass function. So we have x here, and we have -1, and we have 3 here, and we have 4 here, and here we have point here, here, and here. This is probability mass function for x. When we consider probability mass function for y, we have to add to x coordinate of every point here this constant c, in this case 2. It means that all these points will be shifted to the right by 2 units. We see that adding of constant shifts probability mass function to the right or to the left. Another natural transformation that can be do with random number is multiplication by a constant. Again, let c be constant like 2, and now we can consider new random variable z, which is equal to c times x. Now we see that if x takes value -1, then z takes value -2. If x takes value 3, then z takes value 6, and so on. So we have new random variable that takes value -2, 6, and 8 with these probabilities. Again, we can think about probability mass functions. Let us draw the graphs. Now, the horizontal coordinate of every point is multiplied by 2. It means that the whole picture stretches by 2 times. So we have new numbers here. This point goes here. This point goes here. And these points go here. So this is a probability mass function which is associated with new random variable z. Now, let us discuss how expected values change when we do this kind of transformations. Let us discuss some properties of expected value. Let me recall that expected value for random variable with given probability distribution expected value for random variable that takes value x1, x2, x3, and so on, xn with probabilities p1, p2, p3, and so on, pn is defined in the following way. Expected value of x is a sum over all i's from 1 to n pi times xi. So it means that I have to multiply these values by these probabilities and do a summation. Now, let us assume that I have new variable z, which is called to x plus c. What can you say about expected value of z? Or which is the same expected value of x plus c. Let us continue this distribution. For z, the corresponding values are equal to x1 plus c, x2 plus c, and so on, xn plus c. So it means that in this expected value, we can write it in the following way. It is the sum of I from 1 to n, xi plus c times pi. Then we can do basic arithmetic and get the following result. This is a sum, and now we can expand this product and have xi pi plus c pi. Now we can expand it into two sums. The first sum we see that this sum is equal to this expected value. And the second sum we have this c it does not depend on I, so we can move it out of the summation sign. So it means that we have the following equation. Note that this sum is equal to 1, because it is the sum of all possible probabilities, and it means that this thing is equal to Ex plus C. Let me put brackets to make it more clear. And now we see that expected value of x plus c is expected value of x plus c. So we can take this constant out of the sign of expected value. And this is first important property of expected value. Now let us consider second property. How expected value behaves with multiplication by a constant. We can think about the following thing. What can we say about expected value of Cx? Again, we can make x to be defined by probability distribution and now we consider new variable Cx. The values of Cx are equal to c multiplied by the corresponding values of x. So we have Cx1 here, Cx2 here, and so on, Cxn here. Let us calculate the expected value. It is equal to the sum over I from 1 to n Cxi times pi. It means that again we can move this c out of this sum and have the following formula. We see here an expected value of x. So we can conclude with the following. So we see that we can take constant out of the sign of expected value. To conclude, let me write these two important formulas once more. Expected value of x plus c is equal to expected value of x plus c, and expected value of Cx is equal to c expected value of x. These two properties are very important, and we will use them many times. We will begin just right now. We will use these formulas to prove a very nice property of random variable with symmetric probability mass function. Let us discuss symmetric distributions. It means that probability mass function have some vertical axis of symmetry. Let me show you a graph to make it clear. Let us assume that we have a probability mass function that looks like something like this. We have axis of symmetry, which is vertical axis like x equal to x naught. For each value like this, we have symmetric value like this, and our random variable takes this and these values with equal probabilities. So the overall graph is symmetric with respect to this vertical line. In this case, it occurs that we can find expected value of the corresponding random variable without any calculations. In fact, the expected value of x is equal to x naught, at least if it exists. It exists anyway if we have only finite number of values, but for infinite numbers it can be not true, but we consider only case if this expected value exists. Let us prove this fact using properties of expected value that we discussed. First of all, let us consider new variable y, which is equal to x minus x naught. Probability mass function for variable y is related to probability mass function of x. In fact, we just shift this graph to the left in such a way that this vertical line becomes coordinate axis for this new random variable. So if we denote this axis as axis for probability mass function of variable x, then we can introduce new vertical axis, which is probability mass function of variable y. Then probability mass function of y is symmetric with respect to vertical axis. It means that this function is even. The symmetry of this distribution means that the distribution of y is the same as the distribution of negative y. It means that they have the same expected value. So expected value of y is equal to expected value of negative y. Now let us apply rules that we discussed. Negative y is the same as negative 1 times y. It means that this is the same as negative 1 times y, and we can move this negative 1 out of the expected value sign, and in this case we see that it is equal to negative 1 times expected value of y. So we see that expected value of y is a number that does not change when we multiply it by negative 1. The only possible value for expected value of y, thus, is to be 0. Now we can return to our variable x. Expected value of y is equal to expected value of x minus x naught. It means that it is equal to expected value of x minus x naught, according to the first rule that we discussed above. And according to this outcome, we see that this thing is equal to 0. It means that expected value of x is equal to x naught. This is that we announced and wanted to prove. So we finished this proof. Now let us return to probability mass function and discuss why does it work in this way. It is quite intuitive. Indeed, we have this value x naught, and the value of our random variable x can deviate from x naught either in positive or in negative direction. But these deviations in positive and in negative directions are the same. They have the same probabilities, and it means that when we make a summation, they will cancel each other. This is why this value x naught is the actual expected value of x. This gives us some intuition about expected values and how they work. Now we can discuss a new way to create new random variables from existing. Actually, we can apply any function, just a function from set of real numbers to set of real numbers, to create a new random variable from one that we have. So we can say that function of random variable is new random variable. Let us consider some random variable x with a distribution that is given by sequence p1, pn, and values which are given by x1 and so on xn. We can consider this random variable x as a function from probability space to R. Now we can consider arbitrary function from real numbers to real numbers. This is just an ordinary function like x squared or sine x. And now we can consider a new variable z, which is equal to f of x. It means that for every value of x, we can find corresponding value of z just by applying function f. So we have a distribution for z, which is equal to when x takes value x1 with probability p1, then z takes value f of x1 with the same probability p1, and so on. From mathematical point of view, we can say that z is a composition of two functions, function x and function f. Indeed, let us draw a diagram. X is a function from omega to r, and f is a function from r to r. So z is a composition. We have to apply x first and then to apply f. In other words, z of omega is equal to f of x of omega. Now we can find expected value of z. This can be done by using this distribution. We just apply our general rule to find expected value to these values f of x1 and so on, f of xn. So we have a summation we have to take a products of these values by these probabilities and sum over every possible value. So we have this summation f of xi times pi. Actually, we already met this kind of new random variables when we discussed variance. There we found a new variable instead of variable x. We consider it a new variable x minus expected value of x squared. This can be considered as application of a function to this random variable. Now let us discuss some properties of variance. Let us discuss some properties of variance. Let me recall that variance of some random variable measures how far and how often this variable deviates from its expected value. The mathematical formula is the following. Variance of x is expected value of the square of difference between x and expected value of x. We need this square to kill the sign of this expression. So positive deviance and negative deviance now do not cancel each other. So let us discuss how variance behaves with transformations of random variables. First, let us consider a new variable z, which equal to x plus c. Here c is a constant as usual. What is variance of z? We can find it using the definition and the properties of expected value that we discussed before. So this is expected value of x plus c minus expected value of x plus c, and we have to make a square of it. Now we can continue. We can just use the property of the expected value and take this c out of the expected value. So we have the following: x plus c minus expected value of x plus c square. Now we just expand this negative sign. Now we see that this constant cancel each other. So we have expected value of x minus expected value of x squared. This is variance of x. So when we add some constant to a random variable, its variance does not change. This is actually quite natural, because adding a constant will shift our probability mass function to the left or to the right, but it doesn't change on the deviation of values with respect to its expected value. So it does not change, and it is what we expected for. Now let us consider how variance behaves with the second transformation that we discussed, multiplication of a random variable by a constant. So now we have some random variable x, and we have random variable y, which is equal to c times x, where c is a constant. What can I say about variance of y? We can answer this question using properties of expected value. So this is expected value of cx minus expected value of cx squared. Now we can use the second property that we discussed and move this c out of this expected value. Now we have expected value of cx minus c expected value of x squared. Now there is two c's here and here, And we can factorize it in the following way. This is expected value of c times x minus expected value of x. And we have to put square here. Now we see a product of two numbers and a square here. Then it means that we can make it a product of squares. So we have expected value of c squared times x minus the expected value of x squared. Now we can use the same rule with expected values for the second time and move this c out of the expected value because it is constant. So we have c squared expected value of x minus expected value of x squared. And we see that this is variance of x. So this is equal to c squared times variance of x. This is the second important rule about variance. Now let us consider a pair of random variables defined on the same probability space. We can consider the sum of these random variables. How expected value behaves with this sum. We have sum of random variables. Let x and y be some random variables that are defined on the same probability space. And let z be x plus y. What can you say about expected value of z? I want to show that expected value of z, which is expected value of x plus y, is equal to expected value of x plus expected value of y. Let us prove. To do so, I have to recall the definition of expected value of random variable not in terms of its distribution, but in terms of the original definition of random variable as a function of probability space. Let omega consists of outcomes omega 1 and so on omega n. Then we can say that expected value of x is a sum for I from 1 to n probability of omega I times value of x that it takes for omega y. And in the same way we can write expected value of y. It is again the sum for I from 1 to n probability of omega I times y of omega y. Now we can write the definition of expected value of z. Expected value of z is equal to the sum of probability of omega I, and then we have to multiply it by the value of z for given elementary outcome, which is x of omega I plus y of omega I. Now we see that we can expand this product. And we can rewrite it as a sum of two sums. First sum will involve only these terms, and second sum will involve only these terms. So we have sum I we see that the first sum here is equal to expected value of x, and the second sum is equal to expected value of y. So this finishes our proof. We see that expected value of sum of two random variables is equal to sum of expected values. Is the same true for variance? Let us discuss it. Let us consider an example. Let x be arbitrary random variable. The only property we demand from x is that it is indeed random. It means that it has non-zero, or better say positive variance. Let me denote this variance by v, and I demand it to be positive. Now let us consider another random variable y, which is equal to negative x. What is variance of y? According to the rules we discussed, variance of y is equal to variance of negative x. It is equal to variance of -1 times x. We can move this -1 out of this variance, but we have to take a square of this -1. So we have -1 squared times variance, and -1 squared is just 1, so this is just the variance of x. So this is just v. Now let us consider a new variable z, which is equal to x plus y. What can you say about variance of z? Indeed, variance of z is variance of x minus x. Z actually is constant 0, so its variance is equal to 0, because variance of any constant is equal to 0, which is quite natural. So we see that variance of z does not equal to sum of variance of x and y, because variance of x plus variance of y is equal to v plus v is equal to 2v, and it is greater than 0. So we see that in general, variance of x plus y is not equal to variance of x plus variance of y. If you take an arbitrary two variables, then this equality does not hold. But for some special case of independent variables, this can be true. We will discuss independent variables in the next section. To describe interactions between random variables, we have to introduce a new notion, the notion of joint probability distribution. To do so, let me begin with example. Let us consider a random experiment that consists of two tossing of fair coin. And let us consider three random variables associated with this experiment. The first random variable x will be equal to 1 if the first tossing gives us a head. And 0 otherwise. I will introduce a new notation for such kind of events. I will write the condition that we check in square brackets. So the value of this expression, the value of these square brackets, is equal to 1 if this condition is satisfied, and it is equal to 0 if it is not satisfied. So this expression is just a shortcut for this expression. Now let us consider another variable, y. Y equal to 1 minus x. And let us consider a new variable z. Z is the same as x, but it is applied not to the first tossing, but to the second tossing. So z is second tossing gives head. Let us find a probability distribution of all these three variables. We can write it like this. The coin is fair, so the probability of getting head and tail in every tossing is equal to 1/2. So random variable x takes value 1 with probability 1/2, and value 0 with probability also 1/2. The same holds for probability variable y. And the same holds for z. Now, if we look at these three probability distributions, we don't see any difference between these three random variables. But if we think about pairs of these random variables, we see the differences. For example, what is the probability that x equals to 0 and at the same time y equals to 0? This probability is equal to 0, because if x equal to 0, then y is equal to 1. So this probability is equal to 0. Let us ask the same question for pair x and z. What is the probability that x equal to 0 and at the same time z equal to 0? These events mean that on first tossing we have tail, and on the second tossing we have also tail. So the probability of this event is equal to probability of elementary outcome tail-tail, and this probability is equal to 1/4. So we see that similar questions that are asked to the pair of x and y and the pair of x and z gives different answers. This shows us that despite the similarity between their probability distributions, these variables are in some sense distinct. To capture this distinction, we have to introduce the notion of joint probability. Now, let us introduce the definition of joint probability distribution. Let us consider two variables, random variables x and y, let us assume that x takes value x1 and so on xn. We will write it in the following way. Support of x is equal to x1, x2, and so on xm. Support of x is just a set of all distinct values that x can take. In the same way, let us assume that support of y is equal to values y1, y2, and so on yn. Then, for each pair xi and yj, we can ask what is the probability that x is equal to xy and y is equal to yj. So, what is the probability that x equal to xi and at the same time y is equal to yj? We can denote this probability by Pij. Here I changes from 1 to m and g changes from 1 to n. Now, a sequence of these numbers Pij such that all of them are greater than or equal to 0, and the sum of all of them is equal to 1. These numbers, together with these supports, gives us the probability distribution, which is called joint distribution of two variables x and y. Let us consider the example that we discussed before. Let us find a joint distribution of variables x and y. It is convenient to draw joint distribution as a tables, like this. Here we have values that can x take. This is 0 and 1. And here are values that y can take. Here is 0 and 1. And in the cells of this table, we will write these values Pij. So, for example, here we should write the probability that x equal to 0 and y equal to 0. What is this probability? According to the thing that we discussed already, this probability is equal to 0. What about this probability? The probability that x equal to 0 and at the same time y is equal to 1. We can rewrite it as probability that x equal to 0 and we know that y is equal to 1 minus x. It means that if x equal to 0, then y equals to 1. So y equals to 1 is the same thing as x equals to 0. So we see that in this intersection we have the same event, and this intersection is just equal to this event. So this probability is just probability of x equal to 0, and this is equal to 1/2. In the same way, we can show that here the probability is 1/2, and here the probability is 0. Now, let us find joint probability distribution for a pair of x and z. What should we place into this cell? As we discussed before, the event that x equal to 0 and z equal to 0 corresponds to exactly one outcome of our experiment, and the corresponding probability is equal to 1/4. And it is easy to see that all other cells will be filled in the same way. For example, consider this cell. What is the probability that at the same time x is equal to 1 and z is equal to 0? X is equal to 1 means that at the first tossing we have head, and z equal to 0 means that at the second tossing we have tail. So this probability is exactly equal to probability of exactly one outcome, and this outcome is head-tail. This probability is equal to 1/4, just like this one. So we have here 1/4, we have here 1/4, and we have here 1/4. Now, when we look at the joint probability, we see the distinction between y and z when we relate it to variable x. We see that they have different joint probabilities. Joint distribution of two variables gives us information about a distribution of both of them. But what if we are interested only in one variable? For example, let us return to example with two tossing of fair coin. Let us think about this joint distribution. Let us assume that we are interested only in x. What is the probability that x is equal to 0? To find it, we have to decompose this event into two events. Actually, x can be equal to 0 and z equal to 0 as well. The probability of this event is 1/4. But also, x can be equal to 0 and at the same time z is equal to 1. And the probability of this event is also 1/4. So, to find the probability of event that x equal to 0, we have to find a sum of these two values and get 1/2, which is quite expected. We can do it in the same way for any joint distribution and get so-called marginal distribution. This is a distribution of one variable. Let us assume that we have a pair of random variables, x, that takes values x1 and so on, xm, and we have random variable y that takes values y1 and so on, yn. And we have joint probability distribution, meaning that we know probabilities of events like this: x equal to xi, and at the same time y is equal to yj. Here I changes from 1 to m, and j changes from 1 to n. Now, what if we want to find the probability that x equals to xi? We can prove that this probability is equal to sum of the probabilities of this kind. Let me denote these probabilities by Pij. Then this probability is equal to sum of Pi1 plus and so on plus Pin, or in different notation it is the sum like this one. Let us prove this statement. To make a proof, let us decompose this event in a union of events of this kind. If x equals to xi, y can take all possible values, y1 and so on yn. So it means that the probability that x equals to xi is equal to the probability of the following union: x equals to xi and y equals to y1. We have union of several events, and the last event is that y is equal to yn. So y have to be equal to one of these values, so at least one event of this kind will take place. And we also can see that these events do not intersect each other. They are mutually exclusive because y cannot take different values at the same time. So we can apply a rule that the probability of union of mutually exclusive events is equal to sum of probabilities. Each of these probabilities is equal to our probabilities that are denoted by Pij. So we have the sum we expected. This finishes the proof. Now, let us apply this statement to distributions that we discussed before. Let us find marginal distribution for variables x, y, and z using these Gen distributions. For example, for this distribution, if we find marginal distribution of x, we have to find sums of these values. And it is equal to 1/2 here and 1/2 here. Also, if we want to find marginal distribution of y, we have to sum these values. And we have 1/2 here and 1/2 here. This is in the agreement of previously discussed individual distributions of these variables. Now let us look at this table. We have different numbers here, but if we find marginal distributions, we see that, for example, for variable x, we have the same marginal distribution. 1/2 here, which is equal to the sum of these two 1/4, and 1/2 here, in the same way. We can also find distribution of z. To do so, we have to find sums of these values. So we have 1/2 here and 1/2 here. Now we see that having the same marginal distributions here and here, we have different giant distributions. And so it means that in general, if you know marginal distribution, you cannot extract giant distribution of two variables because you don't know how they interact with each other. However, if you know that two variables are independent of each other, meaning that if you know something about the value of one variable, you don't know anything new about the value of other variable, then you can extract giant distribution just by looking at these marginal distributions. We will discuss it later. If you have two random variables defined on the same probability space, these random variables can interact with each other. It means that if you know something about the value of one random variable, then you have some new information about the value of another random variable. Let us consider this example. In this case, if we don't know the value of x and are interested in the value of y, we know that y can take values 0 or 1 with equal probabilities. But if we know that x is equal to 0, we also know that y cannot be equal to 0 as well, and it has to be equal to 1 with probability 1. So, the distribution of y, when you know that x is equal to 0, is different from the distribution of y that we can use when we don't know that x equal to 0 from this distribution. Now, let us look at the pair of variables x and z. Here, the distribution of z is the same. But if you know that x equals to 0, then again you know that z can be either 0 or 1, again with equal probabilities. So, if you know that x equals to 0, you don't know anything more about the distribution of z than information that you had before you know that x equals to 0. You again know that z can be either 0 or 1 with equal probabilities. In this case, we can say that x and z are independent variables. Let us go to a mathematical statement of this definition. Let us consider two random variables, x and y. Now, let us consider the following conditional probability. Let us assume that we know that x is equal to one of these values. What is the probability that y is equal to one of these values? Mathematically, I want to know something about this conditional probability. This is probability that y is equal to yj under condition that x is equal to xi. If this probability is equal to just a simple probability that y is equal to yj, and this equality holds for any I and j, then we can say that random variables x and y are independent. In other terms, x and y as a random variable are independent if all events of this kind are independent for all possible I and j. We can also state the same definition in different terms. As you probably remember, two events are independent if probability of their intersection is equal to product of probabilities. So we can rewrite this condition in the following way. Probability that x equals to xi and at the same time y is equals to yj is equal to product of probabilities that x equals to xi times probability that y equals to yj. Again, this equality should hold for all possible values of I and j. This is alternative and well-known definition of independence of two random variables. Let us return to this example. In this case, this 1/4 is equal to product of this 1/2 and this 1/2. And the same holds for all other cells. So, in this case, if we know that two random variables are independent, then we can find joint probability by multiplication of the corresponding values of marginal probabilities. But in this case, we see that these two variables are not independent. For example, because this 0 is not equal to product of this 1/2 and this 1/2. It is sufficient to find just one cell that violates this condition to say that two variables are not independent of each other. In this example, we discussed two extreme cases. Here, if we know the value of one variable, we know the value of another variable exactly. And here, two variables are independent of each other. But this is just two extremes of a possible spectrum of dependence between two variables. Now, let us consider an example that is in the middle of this spectrum. In these examples, two variables will not be independent of each other, but knowledge of the value of one of these variables will not give us exact information about the value of another variable. We will do it in the next fragment. Now consider a little bit more complicated example of dependent random variables. Let us consider a random experiment that consists of 3 coin tossing. Of fair coin. Now, let us assume that x is a random variable that is equal to number of heads for first two tossings, for first and second tossing. And y is equal to number of heads for second and third tossing. Is it true that x and y independent variable or not? To answer this question, let us construct a joint distribution of these two random variables. We know that variable x can take three possible values: 0, 1, 2, and the same is true for variable y. So let us draw a table for x and y. What is the probability that x equals to 0 and at the same time y equals to 0? If x equals to 0, it means that first two tossing gives us tail, and if y equals to 0, it means that second two tossing also tails. So the only possible outcome that satisfies the condition that x equals to 0 and y equals to 0 is tail, tail, tail. So the probability that x equals to 0 and at the same time y equals to 0 is equal to the probability of one elementary outcome, tail, tail, tail. And the probability of this outcome for three coin tossings of fair coin is equal to 1 over 8. So we have to put 1 over 8 here. What about this cell? What is the probability that x equals to 1 and at the same time y equals to 0? Again, we have to find outcomes that satisfy these conditions. If y is equal to 0, then it means that second and third tossings gives us tail. So the only possible way for x to be equal to 1 is to get head at the first tossing. So the only possible outcome that satisfies this condition is head, tail, tail. And the probability of this event again is equal to 1 over 8. What about this cell? If x is equal to 2, it means that first and second tossings gives us head. But in this case, y cannot be equal to 0, because if first two tossings are head, it is not possible for second and third tossing gives us 0 heads. So this is not possible, and the probability of this event is equal to 0. One can see easily that this cell also contains 1 over 8. But this cell is a bit more interesting. Probability that x equals to 1 and at the same time y equals to 1 is equal to probability that of event that is satisfied by two possible outcomes. Indeed, it is possible to have two heads at the first and the last tossings, and tail here. In this case, here we have one head, and here we also have one head, and this satisfies our condition. But it is also possible to have tail, head, head. In this case, this head is included into both variables x and y. So again, we have one head here and one head here. So this probability is equal to probability of such event. As we have two outcomes that satisfy this condition, the probability is equal to 2 over 8, or 1 over 4. In a similar way, we can see that we have 1 over 8 here, 0 here, 1 over 8 here, and 1 over 8 here. To test is it true that x and y are independent variables, we have to find distributions of x and y alone, marginal distribution. We can do it, for example, for y. To do it, we have to find sums over this row. And we have 1 over 4 here, 1/2 here, and 1 over 4 here. We can see that the distribution of x, marginal distribution of x, is actually the same. Now, to check if these random variables are independent, we have to answer, for example, is it true that this value is equal to product of two values like this, 1 over 4 here and 1 over 4 here? It is clear that it is not true. It means that these two random variables are not independent. However, if we know that x equals to 0, it doesn't give us precise information about the value of y. We see that if x equals to 0, then y cannot take value 2, but it can take values 0 and 1 with equal probabilities. It is different from the distribution of y, but it doesn't give us exact value of y. So, this is an example of a situation when two variables are not independent, but they are not in deterministic dependence between each other. The dependence between them is a kind of probabilistic. It gives us some information about probabilities of y, depending on the value of x, or vice versa. Previously, we discussed that expected value of sum of two random variables is equal to sum of expected values. But, for example, for product of expected values, it is not true. However, if two random variables are independent, then a very natural relation between expected value of their product and product of expected values takes place. Let us consider two random variables, x and y, and let us assume that x and y are independent. Then, expected value of their product is equal to product of their expected values. Let us prove this. Let us assume that x takes values x1 and so on xm, and y takes values y1 and so on yn. I also have to introduce distribution of x and distribution of y. So let me assume that probability that x equal to xi is equal to pi, and probability that y equal to yj is equal to qj. I have to use different letters here to distinguish two distributions. Now, If x and y are independent of each other, then probability that x equals to xi and at the same time y equals to yj is equal to product of probabilities x equal to xy times probability that y equals to yj, and this is equal to pi times qj. This is joint probability distribution that is obtained in this way due to independence of x and y. To find expected value of this product, we have to take into account all possible values that can take x and y and their probability. So, expected value of product x times y can be found in the following way. It is a sum from I and sum over g from 1 to n of probability that x equals to xi and at the same time y equals to yj times values of the corresponding random variables xi and yj. We can rewrite it using this relation. We can say that this is equal to the sum and we put this pi qj here. We have to use double sum here and here because we want to take into account all possible combinations of xi and yj's. Each of this combination gives us a new possible value of their product, and so we have to take into account their probabilities and their values. But now we can separate this double sum into some parts. Indeed, we see that in this sum, these values pi and xi does not depend on the variable of summation g here. They are constant from the point of view of this sum. So we can move this constant out of the summation sign. So we have the following thing. Now we see that this number does not depend on I, and it means that we can move it out of this summation. So we get the following thing. We have product of two sums. If we look at this sum, we see that this is expected value of variable x. Indeed, we have values of x multiplied by probabilities, and we have a sum over all possible values of x. In the same way, this is expected value of random variable y. So we see that this is a product of expected value of x and expected value of y. And this finishes the proof. We see that the crucial point in this proof is the fact that we can express this probability as a product of two probabilities like this. This allows us to move these terms out of this sum and replace this double sum with product of these two sums. If this condition is violated, this proof doesn't work. We will use this fact in the future when we will discuss properties of variance of sum of two random variables. To proceed, we have to discuss variance of sum of two random variables. Previously, we found that variance of sum of two random variables is not necessarily equal to sum of variances. However, it appears that if two random variables are independent, it is true that variance of sum is equal to sum of variances. To prove it, first we have to prove an additional lemma, and also introduce, and this proof also introduce a notion of covariance of two random variables. Let us find variance of sum of two random variables. We will use definition of variance to do it. This is expected value of difference between x plus y and expected value of x plus y squared. Now we can use property that expected value of sum is equal to sum of expected values and rearrange terms in this sum. Now we can expand this square and get the following. Now we can use the rule that expected value of sum of these three random variables is equal to sum of the corresponding expected values. Now we can see that this expected value is equal to variance of x, and this expected value is equal to variance of y. But we also have this term, and this term is called covariance. This part of the term, except of this coefficient 2. This term is called covariance of random variables x and y. Covariance measures some kind of association between x and y. It is strongly related to dependence between x and y, as we will see in the next lemma. If two random variables are independent, then their covariance is equal to 0. Let us prove it. Let us first consider a simple case. Let us assume that expected value of x is equal to 0 and expected value of y is equal to 0. In this case, covariance of x and y is equal to expected value of x minus 0 times y minus 0. It means that it is expected value of x times y. Due to independence between x and y, expected value of product is equal to product of expected values. But both expected values are equal to 0. So their products is also 0. The crucial idea here is that we have this equality due to independence of x and y. In general case, formulas will be a little bit more complicated, but the idea is the same. Now, consider the general case. Let us expand this product. We have sum of 4 random variables. So we have split it into sum of 4 expected values. This is expected values. This is expected value of product x and y. Due to independence, this thing is equal to product of expected values. Here, y is random variable, but expected value of x is just a number. So we can move this number out of the sign of expected value. In this case, we again have product of expected value x and expected value y. And the same thing here. We can move expected value y out of this expected value and again get the same product with the sign minus. Finally, here, product of these expected values is just a number. It is not a random variable, it's just a constant. So, expected value of this constant is equal to this constant itself. So we have plus expected value x times expected value y. We see 4 terms that consists of product of expected value of x and y with different signs. So we see that these 2 terms cancel each other, and these 2 terms cancel each other as well. So the overall, this is equal to 0, as expected. This is finished the proof. Direct corollary of this lemma shows us that if x and y are independent, then this term is equal to 0. In this case, variance of x plus y is equal to variance of x plus variance of y. Now, let us discuss some properties of covariance. Covariance measures some property of association between 2 random variables. Let us discuss some properties of covariance. First, as we discussed just right now, covariance can be used to determine variance of sum of 2 random variables. Second, if 2 random variables are independent, their covariance is equal to 0. Does it follow that if covariance equals to 0, then x and y are independent? Is it true that inverse holds? So, is it true that if covariance is equal to 0, then x and y are independent? Let us consider the following example. Let us consider 2 random variables x and y with the following joint distribution. X takes values -1, 0 and 1, and y takes values 1 and -2. And the corresponding probabilities are the following. Here we have 1/3, here we have 0, here we have 1/3. Here we have 0, here we have 1/3, and here we have 0. Then we can find marginal distributions. For x, every value that it can take it takes with probability 1/3, because here we have zeros. So we have 1/3 here, 1/3 here, and 1/3 here. For y, we have 2/3 here and 1/3 here. It is clear that x and y are not independent to each other. For example, because this 0 is not a product of this 1/3 and this 2/3. But what can we say about covariance between x and y? First of all, we have to find expected value of x and expected value of y. What is expected value of x? We see that x takes value -1 with probability 1/3, 0 with probability 1/3, and 1 with probability 1/3. This is a symmetric distribution, and we see that the expected value of x is equal to 0. Direct calculation shows us that expected value of y is also equals to 0. Now, to find the covariance between x and y, we just need to find expected value of their products. Expected value of these products can be calculated in the following way. It is non-negative, that this product is non-negative if x is non-negative. And the only values for which the corresponding probability is non-zero is this cell and this cell. So this expected value is equal to the following thing. It is -1 times 1 times 1/3 plus -2 times 0 times 1/3 and plus 1 times 1 times 1/3. It is clear that the result is 0. So, we have two variables which covariance is equal to 0, but they are not independent. So we see that the inverse is not true. Now let us discuss some more properties of covariance. Some obvious ones. For example, covariance that of x and y is equal to covariance of y and x. This follows immediately from the definition, because in the definition of covariance we have expected value of product and of course if we swap these terms, the product does not change. Then if we add some constant to x or to y, covariance will not change. Indeed, if we add some constant to x, the same constant will be added to its expected value, and they cancel each other. So, the covariance doesn't change when you add a constant to one of these variables. The same holds for the second argument of covariance as well. Now, what about multiplication by a constant? Covariance of Cx y is equal to C times covariance of xy. Again, this is a direct consequence of definition. Let us prove it. This covariance is equal to expected value of Cx negative expected value Cx times y minus expected value y. As previously, we can move this C out of this expected value, and then we can move them both out of this expected value. So we have C expected value x minus expected value x, y minus expected value y. Now, let us consider a special case. Let us consider a case when y and x are related by some linear relation. It means that y is equal to kx plus b. K and b are constants. In this case, covariance between x and y is equal to the following. This is covariance between x and kx plus b. Now we can use rules that we discussed before and say that this thing is equal to covariance of x kx. Here we use this rule, number 4, and now we can move k out of the covariance using rule number 5 and get k times covariance of xx. By the way, what is covariance of xx? We see from definition that if here y is equal to x, then this term is equal to this term, and we have square of these terms. So covariance of xx is equal to variance of x. So we have k times variance x. In a sense, covariance measure some kind of linear relationship between two variables. If we know that the knowledge that one variable is large gives us some information like the other variable is also large, and vice versa, then they have non-zero covariance. But a little bit better tool to measure this kind of linear relationship is correlation. We will discuss correlation later. Covariance gives us some information about relation between two variables. There is another coefficient that can be used for similar objective, but has a little bit different and in some cases a little bit better properties. This coefficient is called correlation. Actually, correlation is strictly related to covariance. Correlation of two variables x and y is equal to covariance of x and y divided by the square root of the product of their variances. Let us again consider a case of perfect linear relationship. Let us assume that y is equal to kx plus b. What is correlation between x and y in this case? Let us calculate. correlation between x and y is equal to correlation between x and k, x plus b. And we can use properties of covariance now. This is equal to covariance of x, k, x plus b over square root of variance x times variance kx plus b. We know from previous that this covariance is equal to k times variance x. And in the denominator we have the following. Here we have variance x, and here we have some linear transformation of variance. Again, we can use properties of variance. This plus b does not change variance, so we have just variance x times variance kx. K is a constant, and we can move it out of the variance, but we have to take a square of k due to the properties of variance we discussed before. So we have k times variance x over square root of k square times variance x square. Variance is positive, so square root of variance square is equal to just simple variance x. But k can be either positive or negative. So we have k times variance x here over absolute value of k times variance x. Now we see that these two variances in the numerator and denominator cancel each other. And here we have k over absolute value of k. This value is equal to 1 if k is positive, and negative 1 if k is negative. It is not defined if k is equal to 0. So we see that if there is perfectly linear relationship between two random variables, like this one, when you know x, you can calculate y as a linear function of x, then correlation between these two variables is equal either to 1 or to negative 1, depending on the sign of this coefficient k. This makes correlation a perfect measure of linear relationship between two random variables. We will meet with correlation in course of statistics. Let me state some properties of correlation. If I multiply one of the variables for which correlation is calculated, the correlation does not change if this coefficient is positive. It means that rescaling of a random variable does not change the correlation. It is a very useful property. Then, correlation of two variables lie on the segment from -1 to 1. If correlation is equal to plus or minus 1, it means that y is equal to kx plus b, and the sign of k depends on the sign of correlation. If correlation between two variables is 0, it means that the covariance is also 0, and vice versa. So two variables with 0 covariance are also called uncorrelated. As we discussed before, if two variables are independent, they are uncorrelated, but the inverse possibly is not true. As I said, we will return to correlation in the course of statistics, and we will use it as a tool that allows us to investigate relationships between two variables. During this week, we discussed systems of random variables. We considered several random variables associated with the same random experiments. In this case, these random variables can either be independent of each other, or they can interact in some way. For example, random variables can be positively correlated. It means that if we know that one of these correlated random variables has a relatively large value, then the other variable also has a relatively large value, and vice versa. For a small value of one variable, we have a small value of another variable, at least in a sense of on average. This is an example of dependency between random variables. There are also other kinds of dependencies. For example, negative correlation. To describe mathematically systems of random variables, one have to use Gen distribution. It is a distribution that takes into account all possible combinations of values that our random variables can take and attach a probability to each of these combinations. If we have this Gen distribution, we can analyze the relation between random variables. During the next week, we will consider continuous random variables. Discrete random variables are useful to model data like count of something, like number of children in a family. But sometimes we have numeric data that is not a kind of count of something, but just real values, like income or age of a person. And to model such data, to model such variables in the data, we need random variables that can take any possible value, for example, on some segment of a real line, or even any possible real value. Such random variables can be described by probability density function that is closely related to histograms, which is a popular way to visualize data, visualize some numeric variables and its distribution. So we will discuss how to deal with continuous random variables in details on the next week. In this week, we will study continuous random variables. In contrast with discrete random variables that can take only some particular values, continuous random variable can take any possible value from some segment or from the whole line. Why we need them? Consider different kinds of variables that we can find in data. Basically, they can be subdivided into two classes: numeric and categorical. For example, numeric variables are age, or income, or number of kids for some particular person. These are values that have some numeric meaning. And categorical variables are something like education level, or country of origin, or gender, and does this particular person has dog. All these variables does not represent any numeric values. But to study data, we will use some mathematical tools that works well with numbers. In most of cases, we have to recode this categorical data in numeric. For example, we can say that for education level, we have 3 levels, and we can denote school level by 1, college by 2, and scientific degree by 3. Thus, we also have some kind of numeric variable. And we can use random variable to model this variable. And for this variable, we can use discrete random variable because we have only 3 possible values that can be taken with some probabilities. We can also use discrete random variable to model number of kids. Again, we have only particular values like 0, 1, 2, and so on that can be taken with some probabilities. However, if we consider, for example, income, we cannot use discrete random variable to model it because a possible values of income is some segment and not a particular values. So we have to introduce continuous random variables to model quantities like income or age. In this lecture, we'll discuss how can we define continuous random variables. For this, we will use a probability density function, and we'll discuss how it is related to histogram, a popular tool to visualize data. Then we'll use Python to generate continuous random variables and make some probabilistic simulations. We define several notions that we already discussed in context of discrete random variables. In case of continuous random variables, we'll discuss how to define expected value variance or Jan distribution in case of continuous random variables. Finally, we will discuss what is covariance and correlation for continuous random variables and how to use them. Random variables can represent different things. For example, some random variables can represent something like number of heads in a series of coin tossing. This number can take only finite or countable many values. However, it is possible that we need random variable that measures something like temperature or height or some other number that can take any values in some segment or at the whole real line. Now we will discuss random variables of this second kind. Random variables that can take any value from some segment, for example. But to begin, let me recall how we classify random variables. Previously, we discussed discrete random variables. We also subdivide discrete random variables into 2 subcategories. Random variables that can take only finite number of values. In this case, to specify a random variable, we specify its distribution, meaning that we specify which values this random variable can take and with which probabilities. So we have x1 and so on xn. This is values and P1 and so on, Pn probabilities. Another option for discrete random variable is to take infinite many but countable number of values. In this case, we have an infinite sequence of values, x1, x2, and so on, xn, and so on, and infinite sequence of probabilities. Now, we will discuss a new kind of random variables, which are called continuous random variable. Continuous means that random variable can take any possible value, for example, in some segment. Or at the whole line. Now we will discuss how to define continuous random variables. Let us assume that we want to pick a random number from 1 to 0. Or geometrically speaking, we have a segment and we want to pick a random point on this segment. We have a segment from 1 to 0, and our random variable is some random point in this segment. Let us also assume that we want to choose this point uniformly over this segment. It means that, for example, the probability for this point to be at the left half of the segment is the same as the probability of this point to be at the right half of the segment. There is no preference between left and right parts. If we said that we need this point to be inside this segment, then the probability that this point is in this segment is equal to 1. What is the probability that this point is in the left half of this segment? As we discussed, this probability have to be equal to this probability. However, we see that the probability that point is here and probability that this point is here in sum should give us the probability that this point is somewhere on this segment. It means that this probability, the sum of these two probabilities have to be equal to 1. Then both of them should be equal to 1/2. In the same way, we can split our segment into 4 parts. The probability of the event that our random variable is in this part is the same as in this part, and is the same as in this part, and in the same as in this part. It means that all these probabilities have to be equal to 1/4. Using this kind of reasoning, we can decide that for any segment like from A to B, the probability of this point to lie inside this segment is equal to the length of this segment, which is quite natural. The larger segment we consider, the higher probability that our random variable lie inside this segment. However, we have a problem. Let us ask, what is the probability that our random variable is equal to some predefined point, some point x0? We see that we can take an arbitrary small segment that contains this point. The probability that x is equal to x0 is not larger than the probability that x is inside segment from x0 minus epsilon to x0 plus epsilon. But this probability is equal to the length of this segment. It is 2 epsilons. So we see that this probability have to be less than 2 epsilons, and this holds for every positive epsilon. It means that this probability have to be equal to 0. We see the problem. Previously, we described random variables in terms of their possible values and the probabilities that random variable take this particular value. But in case of continuous random variables, we cannot do it like this, because the probability that random variable take any particular value is equal to 0. Now we see that we cannot describe continuous random variables in terms of the probability of their values, as we did it for discrete random variables. However, we can use a different notion, a notion of probability density function, to describe continuous random variables. And just a little note. Here is not the full description of all possible types of random variables. We will study only discrete and continuous random variables. But mathematically speaking, it is possible to consider more complicated random variables. One example of such random variable will be discussed at the end of this week's lectures. And if you want to study the full possibilities of random variables, you have to study some measured theory. This is outside of the scope of this course. As we discussed before, it does not make sense to ask about continuous random variable, what is the probability that this random variable takes a particular value. However, we can ask, what is the probability that our random variable takes a value which is close to some particular number? The answer for this question gives us a probability density function. Let us consider some continuous random variable. And let us consider some particular value x0. How can we ask mathematically about the probability that our random variable takes a value that is close to this x0? We can consider some small segment that is near to x0. For example, segment from x0 to x0 plus delta x, where delta x is some small number. Let us take this segment and ask, what is the probability that x takes a value in this segment. As we discussed before, this probability can become very small when the length of this segment becomes small. However, we are interested in small segments, we are interested in small delta x because we are interested in the small neighborhood of this point x0. So, what can we do? We can divide this probability by delta x. Then, as this probability decreases, this delta x is also decreases. And it is possible that this ratio has a limit. If this limit exists, we say that this limit by definition is equal to the value of probability density function of random variable x at point x0. Now, let us consider example that we discussed before. Let us find probability density function for uniform distribution on segment from 0 to 1. Let me consider some fixed point x0. There are two options. Either x0 is inside of this segment, or it is outside of it. Let us consider first the case when x0 is inside of this segment. Moreover, I demand for x0 to be inside open interval. I exclude these borders of the segment. In this case, if we consider some small segment from x0 to x0 plus delta x, this whole segment is inside of this larger segment from 0 to 1. In this case, probability that our random variable x is inside of this segment is equal to its length, and its length is delta x. So, probability that x is inside x0 plus delta x is equal to delta x. And a probability density function can be defined as a limit as delta x tends to 0, delta x over delta x. Of course, this is a limit of a constant 1. And it is equal to 1. This is the value of probability density function at point x0 by definition. If we draw a graph of probability density function, we see that above of this interval we have constant function which is equal to 1. The second case, when x0 is outside of segment from 1 to 0 can be treated similarly. What is the probability for our random variable to be inside some segment from x0 to x0 plus delta x if x0 is outside of this segment? By definition, our random variable takes values only on this segment. It means that the probability for our random variable to take value here is equal to 0. And it means that if we consider a definition of probability density function, we will also have 0 So the probability density function here and here, outside of this segment, is identical 0. What about these points 0 and 1? It appears that probability density function is not defined at this point, because this limit does not exist. But this is perfectly normal. It is okay for probability density function to have discontinuities of this kind. So far, we defined a probability density function for uniform distribution. At uniform distribution, all parts of the segment have the same probability, provided that they have same length. And this can be seen by the fact that the probability density function is constant over this segment. However, we can consider different probability density functions, and we will do it later. Together with probability density function, we need yet another way to describe continuous random variables. This way is called to use cumulative distribution function. Let x be some random variable. And let us consider the following function. Its value for some point x is probability that our random variable x takes value that is less than or equal to x small. So basically, if we have some point here x, then we have this ray from x to negative infinity, and CDF of x is the probability that x capital is somewhere inside of this ray. Let us consider example of uniform distribution again. Let us pick some point here. What is CDF at this point? In other words, what is the probability that our random variable, which is uniformly distributed on this segment from 0 to 1, what is the probability for this random variable to take a value somewhere here on this array? It is 0. It means that for all points that to the left from this 0, the value of CDF of x at this point is equal to 0. Now, let us consider some point here. What is the probability that our random variable uniformly distributed on this segment has value that is less than, for example, some value here? Of course, if random variable is distributed only on this segment, then it necessarily to have values that are less than this value. So this happens with probability 1. It means that for all points that to the right from 1, the corresponding CDF is equal to 1. What about these points from here to here? We know that for every point here, let this value be x0. The probability that our random variable is on this array is equal to the probability that it is on this segment, because there is no probability for getting here. And the probability of this segment is equal to its length, and its length is equal to x0. So the value of CDF at this point is equal to x0 as well. Therefore, here we have a linear function. Basically, we can say that cumulative distribution function can be written in this case in the following way. It is equal to 0 if x is negative. It is equal to 1 if x is greater than 1, and it is equal to x if x is inside of segment from 0 to 1. Again, we can consider different distributions, and these different distributions will have different CDFs. We will consider this later, but now I want to say that we can define cumulative distribution function not only for continuous random variables, but also for discrete random variables that we discussed on the previous week. Let me consider some random variable . Let me assume that this variable takes value 1 with probability O.2, takes value 2 with probability O.5, and takes value 2.5 with probability O.3. We can write cumulative distribution function for this new variable as well. Let us find its value and draw its graph. Our random variable can take only values 1, 2, and 2.5. It means that if we ask what is the probability that x is less than or equal to some number that to the left of 1, for example 0.9. Of course, this probability is equals to 0, because it is not possible for this random variable to take any values that is satisfy this condition. So this is equals to 0. This is true for every number that is less than 1. So here, values of cumulative distribution function are equals to 0. Now, let us consider case x equals to 1. What is probability that x is less than or equal to 1? We see that x cannot be less than 1, but it can be equals to 1. So, this probability is actually equal to probability that x equals to 1. And this probability is equals to 0.2. This is value of cumulative distribution function at point 1. Now, let us choose any point between 1 and 2. Again, if we ask what is the probability, for example, that x is less than or equal to 1.5, the only possible way for x to satisfy this condition is to be equal to 1. So this probability again equals to probability of event that x equals to 1. So it is again equals to 0.2. And this is value of CDF at point 1.5. The same true for any point between 1 and 2, except 2. So we can draw the graph in this way. Now, let us ask, what is the probability for x to be less than or equal to 2? There are two cases for this event. X can be either equal to 1 or equal to 2. So this probability basically equals to probability that x equals to 1 plus probability that x equals to 2. So we have to sum these two values. And this is the value of cumulative distribution function at point 2. In the same way, for any point between 2 and 2.5, the value of CDF is equals to the same value, 0.7, except point 2.5. Now, if we consider point 2.5 or any point that is larger than this one, and ask a similar question, what is the answer? We know that x can take value only in this set, and every element of this set is less than or equal to 2.5. So the probability for larger points is equal to 1. This is typical cumulative distribution function for discrete random variable. It has several jumps, and each jump corresponds to a particular value that can be that our variable can take. and the size of this jump. For example, this difference is equal to probability of the corresponding value. For example, the difference between this and this is equal to 0.5, and this is this probability. So we see that cumulative distribution function can define random variables that are continuous and that are discrete. It is a kind of universal tool to describe random variables. Let us discuss some properties of cumulative distribution function. We see that cumulative distribution function is a universal tool to describe random variables. So let us discuss a little bit properties of cumulative distribution functions. According to definition, cumulative distribution function of random variable x capital at point x is equal to probability that x capital is less than or equals to x small. This implies some important properties. First, cumulative distribution function is monotonically increasing non-strictly. Indeed, if we have two values, x1 and x2, and x1 is less than or equals to x2, then probability that x is less than or equals to x1 is less than probability that x is less than or equals to x2. This is quite obvious, because if we have x1 here and x2 here, the probability of larger set is larger than probability of smaller set. As we've seen before, cumulative distribution function can be constant on some segments. So this gives us non-strictly increase. But what is important, it cannot decrease. Second property of cumulative distribution function is its limit behavior on minus and plus infinity. As x tends to minus infinity, a cumulative distribution function tends to 0. What is the limit of CDF as x tends to plus infinity? As any possible number is less than plus infinity, this probability that is given by this CDF have to tend to 1. It follows immediately from the definition that CDF can take values from 0 to 1. It is possible for CDF to never take value 0 and 1, but anyway, its value have to be inside this segment, and they cannot be negative or greater than 1, because the meaning of this CDF is probability, and probability cannot be negative or greater than 1. The great property of cumulative distribution function is that, in a sense, any function that satisfies these three conditions, and yet another one technical condition that I will not discuss in details, which is called right continuous. Any function that satisfies this condition defines a well-defined random variable. However, we will only consider, at least a large part of this section, we will only consider only random variables that has probability density function. They are called continuous or, strictly speaking, absolutely continuous random variables. Now, let us discuss the relation between cumulative distribution function and probability density function. Cumulative distribution function is a mathematically convenient way to describe random variables. However, we are more interested in probability density function, because it is easier to interpret them. So, it is important to discuss the relation between cumulative distribution function and probability density function. This relation is mathematically very nice. Let x be some random variable. Let x be a random variable for which probability density function is defined. Let us denote CDF x as F capital, and let us denote probability density function of x as P small of x. Then let us consider some segment from A to B. Probability that x takes value in this segment can be found as a difference between values of f at point B and at point A. What is the value f of B? It is the probability that x takes value somewhere on this ray. And what is the value of this f of A? It is the probability that x takes value somewhere here. So the difference between this probability and this probability is equal to probability of getting somewhere here. Technically speaking, this is the probability not of this segment, but half open interval. Technically speaking, we have to put round bracket here. But as the probability of individual point is equal to 0, it doesn't change anything. So we can replace round bracket here with square bracket here. Now, we can find probability density function in terms of cumulative distribution function. To do so, let us recall the definition of probability density function. Now, let us replace this probability by the difference between values of cumulative distribution function in the endpoints of this segment. We will have this expression is a very well known from the course of calculus. It gives us the derivative of function f capital. Here is delta f, and here is delta x. So this is exactly a derivative f prime at point x. So we see that probability density function is a derivative of cumulative distribution function. This allows us to use PDF to reconstruct CDF. If PDF is a derivative of CDF, then CDF is antiderivative of PDF, and its values can be found by integration. Now, let us recall a fundamental theorem of calculus applied to our functions. It gives us the following: integral over segment from a to b of f prime of x dx is equal to difference between f of b and f of a. Here we have f prime, which is equal to probability density function. So we can rewrite this integral in the following way. It is integral from a to b, p of x dx. This follows from fundamental theorem of calculus. We can provide some probabilistic interpretation of this formula. We know that this difference equals to the probability that random variable takes a value on the segment from a to b. So, if we have some probability density function and we have some segment from a to b, and we ask ourselves what is the probability for our random value to take a value inside this segment. This formula gives us the answer. This probability that x is inside AB equals to the difference between FB and FA. According to this formula, it is equals to integral of probability density function. So the integral is an area of a figure that lies under the graph of probability density function. In fact, this is quite natural. In those points for which probability density function is large, the probability to get a value of random variable near these points is higher than to get value that is in the parts of the line for which probability density function is small. So it is more likely to get point somewhere here than somewhere here when we generate our random variable. More formally, we can say it in the following way. Let us consider some small segment. The probability that our random variable takes value in this segment can be calculated in the following way. From this relation, we can see that this probability is approximately equal to product of this probability density function and delta x. So geometrically, if this is delta x, then geometrically this probability is equals to area of some rectangle like this one. If we split this segment into small segments and construct a rectangle like this over each of this segment, we will have a figure that approximates this figure under this graph. And the sum of these areas will give us approximately area of this figure, which is this integral. So we see that we can use integrals to find probabilities that random variable take values in some segment. This allows us to give a good visual interpretation of probability density functions. Now we are ready to consider some important examples of random variables that are defined by their probability density functions. Previously, we discussed only uniform distribution on segment from 0 to 1, but it is possible to define similar distribution on any segment. Let us find its probability density function. As previously, outside of this segment, the probability density function have to be equal to 0 because no points here or here are possible. As we demand our distribution to be uniform on this segment, the value of probability density function over this segment should be constant. The rest is to find this constant. Note that probability density function have to have the following property. Integral of probability density function over all line have to be equal to 1. Indeed, this integral represents probability that our random variable takes some value between minus infinity and plus infinity. But in any case, random variable takes a value between minus infinity and plus infinity. So the probability of this event is equal to 1. So this integral have to be equal to 1. In this case, outside of the segment from a to b, the value of p of x is equal to 0. So instead of this integral from minus infinity to plus infinity, we can consider integral from a to b. So we have integral from a to b, and the value of probability density function is a constant, and it is equal to p naught. So we have this relation. When we integrate constant, we can just move it out of the integral, and it is easy to see that this integral is just an area of a rectangle for which one length is equal to b minus a, and the other is equal to p naught. So we have b minus a p naught equals to 1, and it follows immediately that p naught is equal to 1 over b minus a. Now we constructed uniform distribution on arbitrary segment from a to b. Probability distribution function is equal to 0 if x is outside of ab, and it is equal to 1 over b minus a for x inside interval ab. Again, this function is not defined at the endpoints of the segment, but this is completely normal. Now, we can consider non-uniform distribution on some segment. Let us begin with segment from 0 to 1. Let me assume that I want a distribution that gives higher probability to get a point near 0 than near 1. In this case, I can choose a different function as probability density function, not a constant over the segment, but some other function that is large here and small here. For simplicity, let us choose linear function. Again, we have a question. What is the value here? Again, this can be found by the same condition as previously. Integral from 0 to 1 of p of x dx should be equal to 1. This integral is an area of triangular And this area, by well-known formula, is equal to this side 1 times this side P naught times 1/2, because it is an area of triangular and not a rectangle. So we see that P naught should be equal to 2 in this case. This is an example of non-uniform distribution on a segment. If we generate points from this distribution, meaning that we do the random experiment and we get a value of a random variable, and we do it several times, we will get some points Sometimes we will get points which are far from origin, but points near the origin will be obtained much more frequently than points far from the origin. And this is what this probability density function says us about this distribution. Finally, let us discuss an example of a random variable that take a value not on some segment, but on the whole line. This is a very well known and a crucial distribution which is called normal or Gaussian distribution. We will consider so-called standard normal distribution. Standard normal distribution has a PDF that which graph is a well-known bell-shaped curve. It looks like this one. So theoretically, for normally distributed random variable, it is possible to have any value on the line. However, the most of the values, the most of probability density is not far from the origin. Mathematically, probability density function for normal distribution is given by the following formula. We see that as x increases, this exponent becomes very small, and we see the same thing on the graph. Normal distribution is a very important example of distribution, and we will meet with this distribution later when we will discuss central limit theorem. Now, let us assume that we have a random variable, but we do not have access to its mathematical specification. We don't know its cumulative distribution function or probability density function. However, we can sample from this random variable. It means that we can take its values several times, and these values are independent of each other. You can think that you can ask a computer to give you values of this random variable, or you can make several measurements of this value and give some independent results. In this case, we can estimate how probability density function looks like. This can be done by histogram. This is a useful tool in data visualization. So let us discuss the relation between probability density functions and histograms. Let us assume that we have a random variable x, and we have a sample from this random variable. It means that we have numbers x1 and so on, xn, which are obtained as values of this random variable. How to find probability density function of x? We cannot do it exactly, but we can approximate this probability density function using this sample. The idea is quite simple. Let us draw a line and let us put our values that are in our sample to this line. So, for example, we have x1 here, x2 here, x3 here, and so on. Let me put some more points, like here, and that's all. Let us assume that it is xn's. So, if we look at this sample, we see that we have 3 points here and only 1 point here. So it is reasonable to expect that in this region, the value of probability density function is larger than in this region, because we have more points here than here. And we can use this idea to draw an approximation to the graph of probability density function. To do so, let us divide our horizontal axis to several segments. Theoretically, these segments should be small, but I don't want to draw a very small segments and use rather large ones. Anyway, let us enumerate these segments, and this will be A0, this is A1, and so on. This is AN, and we also call these segments, this is A capital 1, this is A capital 2, and so on. Actually, this is A capital N. Now, we can say that AK is a segment from AK minus 1, AK. Let us assume that the width of all segments is the same, and it is equal to W. So we have W here, W here, and W here. Now, we can approximate a probability that our random variable take a value, for example, on this segment by its relative frequency according to our sample. What does it mean? First of all, let us calculate values fk. They are called frequencies, and this is just a number of points xi's for which xi lies inside the segment ak. For example, for this picture, f1 is equal to 2, f2 is equal to 3, and f3 is equal to 1. Now let us find relative frequencies. Relative frequency is equal to fk over n. For example, for our picture, we have for values of k 1, 2, 3, we have fk 2, 3, 1. This is the number of points. And the overall number of points is equal to 6. So we have as relative frequency 2 over 6 here, 3 over 6 here, and 1 over 6 here. As you can see, relative frequency is an approximation of the probability of the corresponding event. This follows from the definition of probability. This probability is defined as a ratio of cases when this condition is satisfied and all cases that we consider. So we have this approximate equality. Now we can return to the definition of probability density function. Probability density function at some point, for example at point A, k, is approximately equal to probability that x belongs to this segment over length of this segment. Let us denote this value by hk. So we have an approximation for this probability density function. And now we can write approximate graph of this function. This graph will be graph of piecewise constant function. Over each segment it will be a constant that is defined by this value, so it will be equal to hk. For example, we will have some value here, some value here, and some value here. Note that the height of this rectangle is equal to height of this rectangle divided by 2, because we have only 1 point here and 2 points here. In the same way, height of this rectangle is equal to height of this rectangle multiplied by 3, because we have 3 points here and 1 point here. So height of each rectangle is proportional to the number of points that lie in the corresponding segment. This figure that consists of these rectangles is called histogram, that is associated with this set of numbers. As we discussed here, this histogram approximates the graph of probability density function. In fact, it can be proved that if we increase the number of items in the sample, so n capital, and if we decrease the size of the segment, so this w, then histogram tends to graph of probability density function. This allows us to use samples from random variables to estimate their probability densities. And this is an important tool in visual investigation of data and modeling them with random variables. When we discussed discrete random variables, we considered some properties of these random variables, like expected value and variance. How these properties are defined for continuous random variables? Let me recall that if we have discrete random variable x that have a distribution which is given by its values x1, xn, and their probabilities p1, pn, then we can find expected value using sum from I The idea of this summation is that we find, in a sense, average value of x, but take into account the probability with which these values can be taken. So, for example, if some value has low probability, then its contribution to this average will be low according to its probability. And if some other value has large probability, then its contribution to its sum will be also large. When we speak about continuous random variable, we can use a very similar logic, but instead of summation, we have to use integration. Now, let us assume that x is continuous random variable, and instead of this distribution, x has probability density function p. How to define expected value? Theoretically, we have to consider all possible values that x can take and multiply it by the corresponding probability. But there is infinite many values, and it is not even countable number of values, so we cannot write a sum like this one. Instead,